Yeah, I titled my talk Diffusion, Ubiquitous, and Local, and this is what I was going to do here today. So as in the first part, I was going to define diffusion, and then talk about some fundamentals and try to emphasize why it is ubiquitous. Having done that, I was going to talk about two aspects, which are, as we're doing more and more of these diffusion studies, two aspects that are big potential pitfalls, I think. And I'd like to bring them out and then end with some promise that all of these new things are bringing to us. So let's just start by defining what diffusion is. And if you look up textbooks and things, there are a lot of different definitions you would find. This is the one that I think is very appropriate and I like to use, which is from Onsager. And it says that the motion of a particle relative to the motion of other particles in a defined region of many particles. Now, what does that mean? So if you take, do you see my mouse, actually?
Yes, we can see the mouse pointer.
All right, okay, thanks. So if you take any particular atom, this is a lattice here, but really doesn't matter. If you take one atom here, what you see is that it's moving along randomly respect to all the other atoms in this material, and it ends up at the end in some point here given by this blue arrow. So now with that definition of diffusion, we can say a few things about the nature of the process itself. So first of all, it's a very inefficient motion, at least in the long term. So what happens is it's gone a long way, all these red steps, and then it's ended up only not being very far away from where it was. And if you plot that up in a plot of distance against time, this is what happens. The red line shows what diffusion does, and it's a parabolic curve. So it starts off very fast, but then with time, it just kind of slows down. And as time goes on here, it doesn't get very far. And that was one reason why, for example, the first person, as far as I know, to study diffusion in geology was Bowen himself. And he concluded that it was not an efficient process for any petrologic processes. But the reason for that was he was looking at very long scales. He was looking at the problem of granitization at the time. And on those scales, diffusion is not very significant, not very efficient. However, what you also see here is, and the blue line shows you what happens if you're moving at a constant velocity with something like fluid flow or something. What you see here on the smaller scale, as you start looking at smaller spatial scales or smaller temporal scales, it is actually very efficient and it's impossible to shut it off. And that's the other thing we need to keep in mind. Okay, so second thing is, well, I just said that. So you can distinguish between long-term processes and short-term processes. Over short-term, diffusion is actually very efficient. It's one of these tiny jumps here. And over long-term, you don't get very far. And the final point I want to make on this slide, which is very important, is that this has got nothing to do with equalizing concentration. That's a consequence of all this random motion that's going on, of these atoms that are swinging around. And it is not that if you do not have diffusion, if you do not have concentration gradients. It's the other way around. You always have diffusion. Whether you are equalizing concentration gradient or not depends on that. Now, if you look at materials, this is now computer simulations of a gas and a liquid, and each yellow line is the trajectory of an individual particle. And in a gas, of course, you see them moving randomly all over the place, filling up the space that is available to them. In a liquid, they're also moving around randomly, but there's some structure to it. A given particular atom tends to stay somewhere near its region. And a liquid, of course, has its own defined volume. And if you do the math of all of that, things moving along, you end up with this famous Gaussian curve, which tells you that if you start off with all your atoms concentrated at the 0 point in the beginning, then things will spread out with time in both directions along this Gaussian curve. Now, one important point that also comes out of this math is that If you have other processes going on, fluid flow and so forth, then what happens is that this whole Gaussian curve moves along. So it's displaced here, but you do have a diffusion, again, on some scale, you have this diffusion process. You do not shut it off. You do not turn it off ever. Now, when you get to solids, it gets a little trickier because solids don't have atoms that are moving along randomly. So that's gas and liquid here on the left. And the solids have atoms that are sitting and vibrating around in any particular lattice positions. And if you try to work out the math here, you'll find that things do not actually or should not diffuse, because you cannot, the atoms are not here in the middle because it's energetically not easy to be here. And they cannot possibly hop into another place where there's something already sitting there. So the only way you actually have diffusion in a solid is because you have defects in solids. Now you can have many different kinds of defects. One of the most common ones is a vacant site. You have a lattice here with one site where there's a missing atom, a vacancy. And there, it's energetically more convenient. It's a lower energy point where an atom can possibly hop. And you can then again do the math of that hopping, how often these atoms are trying to make the jump, what's the height of this energy barrier, and so forth. And you come up with a formula that defines just one kind of diffusion coefficient. Now, what also comes out of this is how this diffusion coefficient depends on temperature. And that's basically because, I'll just go back once quickly, because these energy barriers here, they change with temperature quite strongly. So now if you have that temperature dependence, that's given in this form called the Arrhenius equation, where you have a pre-exponential factor and an activation energy. Now the point I wanted to make here is that if you look at the process that I was just showing in the last slide, where one atom is jumping over to a vacancy, or in a case of a liquid or a gas, to the next possible location. The activation energy is related to the energy barrier that it has to jump across. But when you actually do a macroscopic process and then you look at atom diffusing in a solid with a vacancy like that, turns out that this activation energy has different other contributions to it. So for example, you'll have the energy required to make or enter the vacancy, or to fit in an interstitial space, and so forth. So that all gets lumped together in this one macroscopic parameter. The same thing with this pre-exponential here. It depends on the frequency of the atomic jumps. It depends on the vibration of frequency of the atomic vibrations. It depends on the distance, the jump distance that you have, and the entropy change that you cause by diffusion. All of those things go into these things. So the main point is that given these quantities, these atomic properties, you can say what will and will not affect diffusion rates. But given a value for D0 or Q, it's not a trivial matter to get one of these things out of that. Can be done, has been done, but it's not a one-to-one correlation. Okay, so if you have that kind of dependence, you can plot it. Okay, so what I also wanted to do was to mention quickly the different factors that can control diffusion coefficient. You mentioned temperature, which is by far the strongest effect that you have. It's a very thermally activated process. And what that means is, in terms of diffusion studies, you need to worry about where you have non-isothermal diffusion. Now, you have already heard Tommy talk about one example of that. The other factors are, pressure can affect diffusion. Composition plays a very important role. You cannot take diffusion data for olivine 90 and start modeling something at phosphorite 60. In crystalline matter, because it depends on the jump length and so forth, anisotropy of crystals plays an important role. Fluids can affect diffusion. Things like oxygen fugacity control how many defects or vacancies you have in a crystal. Water can do the same sort of thing, so they can affect diffusion rates. The state of strain of a crystal, how deformed it is, can affect diffusion in many different ways, actually. And you can have many different diffusion mechanisms. So those are the different factors that control diffusion. I'll just focus on temperature for one more slide here and show you something. Oh, sorry, so I forgot. So if you take all of these things together and try to describe a diffusion rate, you end up with expressions that look like this, which are quite long expressions, but what you have here is a p exponential factor here, an activation energy kind of term, which has got many other components built in here, pressure and volume and so forth. And all those dependencies on fluids and other chemical components come in through terms that look like that. And you have these parameters M, L, N, and so forth, which you then try to determine experimentally. And so you've done that for many people that worked on these and produced many of these data. One of the things that we have produced is in olivines as a result of a lot of experiments. I'll show you that in the next slide right away. But you see that, for example, XFE becomes here to the power of 2/3, activity of silica becomes to the power of 1/6, and so forth. And these things here are what I was talking about, the activation energy, but it is made up of different terms in there. And that value happens to be for olivine, this number here. The pressure dependence similarly depends on different individual microscopic mechanisms, but the overall dependence is this number here. And if you plot all of them up on a temperature diagram, that's what it looks like. And there are 2 points I want to make with this diagram here. Now, first of all, it depends strongly on temperature. You see that, it is going from about 1400 to 1500 degrees to close to 600, 700 degrees. The diffusion coefficient changes by 7 orders of magnitude. Okay, so it's a very strong temperature dependent process. But the important thing is this dependence is nonlinear. So if you look at the temperature axis on the top, going from 1400 to 1300, you change the diffusion coefficients, of course, but not a whole lot. Whereas if you go from 800 to 700 or 600, it's a much bigger change that you go through. And that's something you have to keep in mind. So in a lot of things we do in volcanic systems, in magmatic systems, we often get away with using a constant temperature because we're up in these high temperature regimes. Now, if you do more accurate work, you do have to worry about temperature dependence here, and you'll hear about talks tomorrow, I think, which do deal with that. But if you get down to the metamorphic regime below 800 degrees, you have no chance but to worry about the temperature dependence of diffusion rate. So that's something that we need to think about in terms of applications, high temperature versus low temperature things. High temperature things are a little bit more forgiving. Okay, now I've done all of this without mentioning Fick's law and without mentioning concentration gradients, and that's on purpose. So the whole point is, again, diffusion is something that's random, that's going on all the time. And if you happen to have a concentration difference, like shown here, high concentrations on the left, low on the right, then this random motion causes the concentration to get equalized. And that's what's described by Fick's law, which tells you that the flux of atoms in moles per square centimeter per second or something is proportional to the concentration gradient, and the proportionality constant is the diffusion coefficient. If you look at that description a little bit more carefully, you see a couple of things. So the slope, that's dc dx, at different points along the profile is quite different. So, the purple line here is quite different in slope from that one there, which means that along one such profile, the flux is different at different places, okay? And if you stay at one particular point and look at how the profile evolves, you see that the slopes change as well. So the flux changes at any given place as a function of time as well. So that brings me to the second very important point. First of all, diffusion is ubiquitous. It happens all the time, everywhere. And the second point is it is local in space as well as in time. So the flux that you have, even along a given profile, a constant diffusion rate and everything, will be different at different points and different places. Okay, so those are two things that are important to remember. And then the last point I had in terms of introduction here was this one here, looking at a rock. And what you've been looking at so far is kind of looking at diffusion within a crystal, a lattice plane around here. Now you've heard Katerina's talk. You've heard a lot about grain boundary diffusion. So I don't need to introduce that anymore. But the point I wanted to make here perhaps is that even if you have a rock with grain boundaries and surfaces, then you can treat that whole thing as a representative elemental volume, as one sort of averaged volume of some sort. And you can look at the flux of atoms coming into this volume and going through all of these different individual steps, diffusion within the lattice along different directions, diffusion in grain boundaries, diffusion on the surface, and average all of that, and you get a flux that comes out. And you can treat that process also using a diffusion equation. So it's just the randomness that's really the key to it, and not whether you have lattice or grain boundaries or volumes or not. You just have to have enough to make a statistically meaningful average of a random process. And so much so that the other area where diffusion equation is used a lot in geosciences is in geomorphology. The erosion of hill slopes are modeled by exactly the same equation. And there, of course, you don't have lattice or an atomic diffusion process, but you can describe the process by a diffusion equation nonetheless. So it's really the randomness that's the key. The equalization of concentrations is something that just happens as a result of that. Okay, so with that, I was going to get to two pitfalls as we get into more and more sophisticated handling of these things. We also run into more trouble or things that we need to watch out for. So the first one of this is this business here. Now, diffusion length scale S is given by the square root of d times t, so square root of the diffusion coefficient times the time. And because we are interested more and more in shorter and shorter time scales, we're keen to go down to shorter and shorter diffusion profiles. Okay, so smaller the t per given d in a given element in a given mineral, the smaller is the S. And in the past few years, we've had a number of different ways of analytically accessing this property. So for example, we have atom probe tomography, which I show pictures of here on the left from a metallic alloy. You see things on a grain size scale of 10 nanometers or 40 nanometers. You can measure concentration distributions here. You can look at analytical transmission electron microscopy. I assume Katerina talked a little bit about it already. Here I have another profile in an olivine over a distance of a micrometer, but you can go way below that in ATM. You have nanosims that gives you very high resolution concentration profiles. And you can look at image analysis using backscatter electron images or cathodoluminescence images. And from that, you can extract very sharp, very short concentration profiles. Now, people do that. People have been using these to get timescales, model diffusion, and there is a problem. So let's go back to our Fick's law. Let's go back to what we were doing here. We were looking at this red concentration profile. We're looking at the purple slopes here, and that gives you the flux and the diffusion rate and so forth. Now, what happens at the beginning when you have this steep gradient here? What is your dc dx at this discontinuity? It's actually not defined. So that's a trick that we sort of gloss over when we teach this kind of concentration profile Fick's law thing, that Fick's law actually does not apply right at the very beginning. Because if you put in an undefined large concentration gradient, your flux would be infinite or something, and you'd homogenize everything right in one go. But it's not even infinite, actually. It's really undefined at this point here. It's a singularity. So how do you deal with that? You do this. You go and look at the atomic process. So you look at the lattice planes. These are now red atoms and white atoms. And they're jumping from one plane to another with some frequency. And you count your atoms. So your plane n and n plus 1 and 1 before n minus 1. And the rate at which things are moving from plane 1 to plane 2 is this gamma 1, 2. The rate at which it's jumping back in the other direction is gamma 2, 1. So you can define an average jump frequency gamma s, that's an average of the two, and so forth. And then you can do a simple bookkeeping. You can just go and count the number of atoms. You see how many atoms are coming in from left to right and how many are leaving from right to left. And you take the difference and you end up with an equation that looks like that. That describes diffusion in such a lattice plane kind of a atomic setting without assuming any statistical averaging and defining a concentration in a volume. Yeah, I mean, concentration is always in a volume. If you have only one atom, you cannot define concentration. Now, if you have that, let's see what diffusion looks like. So if you take a concentration profile, which is a sine curve, let's say, like this, and take it through the diffusion equation, take a solution, you would find something like that, a sine curve that looks like that. If you work out the Fick's law solution, if you apply Fick's law to it and get a solution, you will find that your alpha would have to be related to the diffusion coefficient by a factor such as this, where this big lambda is the jump distance here between the planes. And you can also go and do your atom counting, right? I mean, you can go and count your atoms and do your things, and then you get a different formula. It looks like that, okay? So the mathematical problem is, of course, very straightforward. So you basically want both of these to give you the same answer. And if you do that, you find that you have to do a little bit of algebra to get to this. But what it tells you is that if your jump length here, the length over which you're measuring your profile is, sorry, not the jump length, the wavelength of your concentration profile. So basically the concentration profile that you're measuring, if that is 10 times lambda, where lambda is the lattice plane spacing, yeah, then these two formula give you the same answer. And if you go and look at that for olivine, this is what you get. So along the c-axis, the lattice plane spacing is about 10.5 angstrom. And what that tells you is that you need about 10 to 15 nanometers of a profile before Fick's law can be used. And actually, you're better off taking a little bit more than that. Factor of 3 or 4 more than that. So what that means is that that's your first pitfall. So analytically, we can now go in and measure concentration profiles at length scales that are much below these nanometer scales. But, and we can also model diffusion in those, but we should not use the usual Fick's law model to do that if you get down to such high resolution. Now you have other issues at those high resolutions, and here's another one. So this is something that we can produce in our lab, where we take olivines and we can make thin films of olivine. Now these are produced by this technique of pulsed laser deposition. And this is now a film of olivine on another olivine, where the film has a different isotopic composition. And we didn't go and measure that. We don't do anything, no diffusion, nothing. We've done that at room temperature, just put one olivine on another. And if you go and measure that on an ion probe, you see profiles that look like this, the black one and the red one, depending on how you're measuring things in the ion probe. Now, this not only look like diffusion profiles, they are actually, again, a random mix of roughness that you have on the surface and other effects that you have in analysis. And the form is exactly a diffusion profile. You can actually fit that with the diffusion coefficient, and you'll get time scale 6.2 hours, or for the black one, you get 56 hours. And these are, of course, meaningless time scales. These are no diffusion has taken place there. It's just an analytical artifact. So again, if you're going down to really, really small diffusion coefficients, if your analytical techniques are getting better, that's something we need to, these are two things we need to worry about. First, to make sure what you're looking at is a real diffusion profile, not the analytical resolution of your instrument. And second, to check whether you should be using Fick's law to model those diffusion profiles. Okay, so with that pitfall, I'll get back to the second pitfall that I plan. And I heard Tommy talking about the problems he has with moving boundaries. Well, it's not just him, everybody. It's a messy situation, but let's go look at that a little bit. So if you have a very general situation, you have a crystal that's interacting with the fluid, You have fluid flow, where you have advection and diffusion in the fluid. You have, in the crystal, you have dissolution, precipitation, and diffusion. That's all the processes that can go on. Now, the first thing, and you're producing a reaction product by growth or dissolution or whatever. Now, the first thing you want to do is make sure that you have mass balance, and you do that so all of these processes here cannot be independent of each other. Because anything you want to diffuse, if you want to dissolve something, then the composition has to be updated by things diffusing in from the inside and so forth. So you need to look at all of those together. Is the first thing. Second, because minerals are generally solid solutions, unless you're dealing with quartz or something, solid solutions have this property. I've shown this here on the bottom. Any phase diagram as a function of any intensive variable, pressure, temperature, oxygen fugacity, as a function of composition, has this famous cigar form, which tells you that when you, in this case, if you heat something up, the reactant and the product has to have different compositions, okay? And the moment you have that, okay, so you're starting with something and you're producing something where the relative proportion of atoms are different. You remember the definition of diffusion, you got to have diffusion somewhere, somehow. So without diffusion in the fluid or in the solid or in the mixed zone between the solid and the fluid, unless you move atoms relative to each other, you cannot change compositions, okay? So then, if you look at that situation mathematically, you end up with equations that look like that. So what ends up happening is your diffusion law would have been this, and now you have a growth or dissolution that adds another term to the whole thing. And if you look at the solution, depends on how your the boundary conditions and so forth. But what ends up happening is, your normal diffusion would give you as a solution this kind of term here, an error function term. What ends up happening when you have growth and dissolution is you have a second term that comes in. So it becomes a sum of two different things rather than one thing. And that causes a number of differences in the nature of the behavior of the systems, which I want to talk about a little bit. So first of all, right, so let me try this now. Instead of showing you a lot of panels, I thought I would have a little bit of time. I would actually show you what this equation does, and that's a lot easier than trying to tell you what things do. So now I have to worry about sharing again. I'll get out and share a different screen now. Are you seeing an Excel sheet here?
Yes.
Okay. So what I've done is I've programmed in that formula. And here I can enter a value of d. Can you read that, or should I make that a little larger?
It should be fine.
It's fine. Thank you.
So you have a diffusion coefficient here, and you have a growth or dissolution rate here. And what I show you here is a concentration profile. And for a diffusion rate of 10 to the minus 13 meters squared per second, you have some kind of a profile that you see here. Let's just go and try to change that. I'll make it diffusion faster, 10 to the minus 12, and you end up with a straight line that looks like that. Now the axis here will be changing, but the form of the profile stays the same thing. So it's 10 to the minus 12. I can make it 6 orders of magnitude faster, 10 to the minus 6. And the axis changes here. The shape of the profile stays exactly the same. Nothing changes. Now I can go and make it slower. I can make it 10 to the minus 13 again. You start seeing a little bit of something that looks like a concentration profile. If I make it a little bit slower yet, then you see a real diffusion profile. And slower yet, 10 to the minus 15, it's gone. Now you have no diffusion, you just have a thing that's looks like a flat profile. If I go much slower now, 10 to the minus 18, nothing changes. So the message I want to give you is that if you have dissolution and growth occurring together, there's only a tiny, tiny window where you actually see a diffusion profile. All right. And you can do the same thing. Tommy was talking about how you need to balance diffusion and growth, and you can really play with this very easily here. So now I'll leave the diffusion at 10 to the minus 13. I can go and change the growth from 10 to the minus 6 is what I have now. And if I change it to 10 to the minus 5, you get a profile. I make it 10 to the minus 3. It's all gone. If I go back slower, 10 to the minus 7, you go back to that straight kind of a gradient and nothing. So it's really a very small window of growth rate and diffusion rate where you actually see a diffusion profile. Now, what that means is if you don't see a profile, it doesn't mean that diffusion was not happening, okay? So I have summarized these things in the next slide. So I need to go back to my PowerPoint again. Give me a second. So am I back on the PowerPoint?
Yes, you are.
Yes.
Okay. So you see concentration profiles when you have growth and dissolution occurring with diffusion. That's a very, very common situation. I mean, it's rare that you have a crystal just sitting there and diffusing and not doing anything else. So first of all, you will see profiles only for a small range of value of D and V, the growth or dissolution rate. For a given diffusion coefficient and too large or too small growth or dissolution rate, you won't see a concentration profile. So if you do see a concentration profile, you are pretty safe. But then the question is, how do you model that one? Because the concentration profiles can get a little distorted. So that's something we need to worry about. And then we need to sort of know what this V is. And that is the problem, because actually doing the calculation is difficult, but doable. The problem is knowing how fast or slow things are growing and dissolving. But if you see a step profile or if you see a sharp boundary, that does not mean there was no diffusion. So that's the message I wanted to give you. Now, it gets even trickier than that. So that was the equation. Now, if you have that equation, you can go and set the change of concentration with time to be 0, a steady state. You don't have any change going on. What that means is, again, what Tommy was saying in words, your diffusion flux has to balance the flux occurring by growth and dissolution. Now, that is something that can happen. And you saw that happen. You saw that, sort of a straight gradient came up, which doesn't seem to change much with time. And that is a new feature of a system where you have growth and dissolution with diffusion. You can reach a steady state, and then you have lost all information on time. So this is now the reverse. You have diffusion. You can measure the diffusion, but it is not a function of time anymore. So you have a profile. You can fit that, and you could get a number out of it, but that may be, again, a meaningless number. So that's a third thing that I'm telling you, where you have a profile, you can fit that, and you can get either meaningless number or no number. So after talking about trying to do diffusion modeling to get timescales for many, many years now I'm telling you all the cases where you need to watch out and not do diffusion modeling, because we're beginning to hit those limits in many cases now. Now, the reason you have that problem is I have a picture here. So this is two pictures of manganese element maps in garnets. And this one particularly is quite spectacular. And what you have from the shape of this thing, you can tell that the garnet was, something like this. And the way we think about this is when this resorbs, then the manganese just goes back into the garnet because it prefers the garnet. And I can sort of run this here. So that's what happens. So you start with a garnet, you produce this kind of smaller garnet with manganese enriched in the rim. Now you can model that. That's no problem in terms of mathematically doing it, but it becomes very, very critically dependent on how quickly it's getting resolved. As you just saw, if I change the value of V and D, I can get all sorts of profiles. And that is what has been a challenge, why these sorts of profiles are spectacular, but we are not able to get good timescales from those things in many cases. So something to work on, to try to get a handle on the growth and resorption rates. Okay, so having done all of these things, I want to end the talk on something that's more promising, something that gives you hope of something that you can do. And for that, I want to go back to the Dawson equation, because that is one of the most widely used equations, but it's also one of the most widely misunderstood equations as well. And what I've put up here is the classic Dawson equation, the form in which it is used most commonly. You have a diffusion rate that goes in here, you have a grain scale, cooling rate, and so on and so forth. Now, the first thing I want to do is to point out that Dawson did not actually derive that right away. What he derived more generally was a thing at the bottom. And he derived that for a time constant and a rate constant K0, which applies to any kinetic process. Now, anything that's kinetic depends on that Arrhenius kind of equation that I was showing you before. And as long as you have that Arrhenius kind of equation, you can use the Dawson equation in its raw form. It's only when you get into this form that you have made many different assumptions which may or may not be valid. I think Tommy was talking about it at the beginning. I missed that, I don't know, but I'm sure Claire and others will come up with that. But I wanted to point out some of the assumptions that do go in the usual Dawson equation. One of those is a fact that it's a so-called linear thermal history, by which Dawson meant that 1 over T increases linearly with time, not temperature. And I'll talk about that in the next slide, so I'll leave that for now. The other big condition is that it has to be, you can apply that equation only when it's sufficiently removed from the peak temperature. If you look at all the terms in this equation, if you go back to the previous slide where I had listed what each of these things are, you would see that there's nothing that defines the initial condition in here. And that is because it was derived assuming that the rock or the mineral has forgotten the starting condition. It has diffused enough to do that. If it has not, then you have to do something different. Thirdly, you need to have a crystal that sits in a matrix where transport is infinitely fast. So anything that wants to diffuse in and out can do that. Now, the thing that Tommy was showing, the clinopyroxene in a garnet, where diffusion is slow in both of those, you cannot go and use that equation right. You can use a raw Dawson equation and apply it to different points and different places, but not this formula straight away to those equations. And it's ideally suited for a trace constituent, so for a place where you have no coupling effects or multi-component diffusion or something. So with that, I'll come to this linear thermal history part. Well, what that tells you is that if you have a complex thermal history, temperature, time history here, and your closure temperature according to the Dawson equation here, then it is giving you the cooling rate and the thermal history of the rock right around this region. By definition, it has no memory of what happened before, and it doesn't, of course, know what happens afterwards. So it's really a small window where you can get information from the Dawson equation, and that's something we need to keep in mind. If we do that, we have the advantage that we can use different rocks, different minerals, different elements with different diffusion rates in the same rock, and try to reconstruct a nonlinear thermal history such as this. And I'll show you that in my last slide here, which is busy, but let me tell you what's going on here. So this is a diagram, a schematic diagram I had in this paper from back in 2006, where I made the point I just told you in words before, that in a rock, in a thin section, you have many different minerals, different colors. In each mineral, you have different elements which diffuse at different rates. And so you have a lot of options of doing statistics, doing cross-checking, seeing whether your results are meaningful or not. And you can then use them to reconstruct different segments of the thermal history. And in the remaining plots here, I've just put three papers that we wrote at different times, where we did make use of different aspects of this to get into nonlinear thermal history. So here you have a Proterozoic mobile belt. These were granulites, where conventionally, actually the published result was one of these red dotted lines that you are cooling along that range. But modeling this using the local nature of diffusion, we could see that there was a thermal spike in between here. Now, this is something completely different. This is Kati Fick looking at oceanic crust in gabbros. And again, depending on the cooling rate, you're freezing the same system, magnesium in plagioclase in this case, at different temperatures at different distances from the gabbro. And if you look at that in that sense, the whole data set makes a lot of sense. If you start saying that, oh, different grains are giving different cooling rates or different freezing temperatures, then you seem to not get much meaningful out of it. And finally, this is from Sikkim Himalaya, where we took the high temperature history from garnets and diffusion modeling and lutetium hafnium dating. And we couple that with low temperature histories from fission track in zircon and apatite, and you can construct quite a robust nonlinear history out of that. So that's really a power of this thing, because diffusion is local in time and space, and it allows us to get to these nonlinear thermal histories now, which we were not able to do even a few years ago. And with that, I'd stop my talk today. Thank you. Thank you again for all your patience.
Thank you, Sumit, for this very exciting talk. And yeah, the chat is open for questions. So Sumit, Bruce is asking, you have pointed out the pitfalls in getting time information from closure, but as zoning gets worse for estimating rates, does it get better as an indicator of temperature?
Yeah, the original Dawson statement coming from someone in Leeds, it depends on the system. So it depends very much on the activation energy. So if you have processes with high activation of energy, yes, it can become sensitive to temperature, and you can use it to increase temperature. But if you have processes with low activation energy, then the whole thing gets much more smeared out, and it is not very good for getting temperature. But in some cases, yes, you can.
So, do you say that that the diffusion community should not participate in the hunt for higher resolution analytical profiles because we are basically stepping out of our skill zone, if you like?
No, Tommy. What I'm saying is you should broaden your skill zones. By all means, go to the highest resolution that you can analyze. You should just make sure that your modeling tools evolve with that and not just stick to Fick's law, because that's what we used to do many years ago and have been doing for a long time.
Yeah. And I think one of the important points is really to recognize what can be done by diffusion modeling and what can't be done by diffusion modeling.
Exactly. I mean, I guess if there's one message that I'd like to repeat again is that diffusion is just present everywhere all the time, but we need to pick out what we can model, what can give us meaningful information on either time or temperature. And one of the things, again, I think you were talking about in your talk is So, if you have growth and dissolution and diffusion and you have a profile and you're not sure whether it's a steady state or not, whether it's giving time information or not, one thing that we have in our hands is that we have many different elements, and these diffuse at different rates. So we can use that to check whether something is hitting steady state or not. But we need to do the work. That's the message.
Yeah. And this is the occasion for me to remind or to point you to Claire's talk tomorrow, because we basically, evolve into the thermochronology, and Claire will give a very interesting talk tomorrow morning, tomorrow in the first talk. You know what I mean.
Hopefully it's not tomorrow morning. I hope it's tomorrow afternoon.
It is tomorrow afternoon. I'm in conference mode, right?
We've got to get rid of all our hangovers from all our beers tonight before.
So are there more questions? If that's not the case, thanks again, Sumit.